Hello everyone and welcome to this video on programmable logic array. In this video we will be discussing on how to design a programmable logic array and how to build the Boolean functions onto a programmable logic array. So the outcome of this lecture would be helping the students, and the students would be help get knowledge on PLAs, and students would be able to explain the PLAs and its working and able to build an Boolean functions using of PLAs. So this is the concept which we have discussed in the previous class, like programmable logic devices. So under the programmable logic devices, we have discussed on programmable read-only memory or PROM. So programmable read-only memory is such a way that AND array is programmable. This is programmable. You can have an user's concept over here in the OR array, but AND array is fixed one. AND array is fixed. OR array is programmable. Going to the today's topic of interest, which is nothing but PLA. In PLA, both AND array is programmable or array is programmable. So in the previous class, we have seen when you go for the PROM, we have taken all the meanterms. All the meanterms is nothing but we have taken a simple decoder. If the number of inputs are 2, we have taken 2 cross 4 decoder. If the number of inputs are 3, we have taken 3 cross 8 decoder. So the decoder was there like this way. This is 2 cross 4 decoder. You have taken 2 cross 4 or 3 cross 8 decoder. But when you go for PLA, number of gate, to say, will be less than the number of inputs. No, I mean to say, if number of inputs are k, the number of product terms would be less than, it won't be equal, it would be less than 2 per n. It depends on your given functions. If all literals are there, automatically all the terms will be there. Otherwise, it will be less than that. Each number of AND gates can be programmed to generate a product term, and this one, the fusing concept would be also be there. And obviously, these Boolean functions are represented in the sum of products form. Okay, by probability links. So this would be the general structure of an PLA. Either starting with an input, one input would be the true form, the other would be the complementary number. Here the fusers would be there. According to the fusers, you will be generating the AND gates functions. How many AND gates are required? Those many AND gate functions would be there. Then followed to that one, you would be having a OR gates matrix. So then we have OR gates. Then last one, you would be having the output can be connected with the links of 1 or 0, which is nothing but using exclusive OR gate or AND gate, get and true or output form. So here PLA has M outputs and number of OR gates is equal to what? M. If your outputs are M, then number of OR gates is also M. Number of now output of each OR gate gets to the XOR gate, where output has two links. One is logic 0 and logic 1. So this would be the simple structure. How would be that? Now you can see both are programmable. This is rough figure where all the fuses are intact. Is the PLA rough PLA. So to this PLA, what we'll do is that we'll go for taking into consideration. This is the fuse concept example of this one. Some of the fuses are kept intact, some of the fuses are blown away. This is the general structure. You will be having output also, you will be connected with the fuse links. These are the fuse links. At the OR gate, we are having the fuse links. At the NOT gate, two terms will be coming out. Each would be having the number of inputs to the OR gate AND gate is equal to 2 times the number of inputs given to the PLA. And number of inputs to the OR gate is equal to number of product terms which are coming over here from the AND gate. So then you are having one OR gate. So when we go for a simple example, we take into consideration implementation of full adder on a PLA. So coming to the full adder is a circuit which is having 3 inputs and 2 outputs. So the truth table for this one is given like this way. This is when you add two numbers, to say 0 plus 0 plus 0, sum is 0, carry is 0. When you get 0 plus 0 is 0 plus 1 is equal to sum is 1 and carry is 0. This is 1 and carry is 0. 0 plus 1, 1. 1 plus 1 is nothing but sum is 0, carry is 1. Okay. So like this way, if you proceed it up, you will be getting the truth table line, which is shown over here. Now, when you want to get the equations of this one, will be putting up this one into the key map and deriving for the equation. The sum expression is being given as A exclusive of B exclusive of C. And similarly, the carry expression, when you solve for this one K map on the three variable K map, you will be getting carry out is equal to AB plus BC plus CA. These are the three inputs you have. The sum expression, which can be expanded over here as A prime B plus, sorry, A prime B, A prime B prime C in plus A prime B C in prime plus A B A B prime C prime plus A B C in, which is equal to the same thing. Or wherever you had the term as one, we can write as this. So this is the expression for PLA. So the PLA programming table is been given over here. We will be designing this one. Both the inputs sum and carry are taken at the true inputs or true outputs. So this is the PLA programming table. That's the expressions we will write it up. Totally, how many terms are there? Product terms are 7. So number of inputs are 3, number of product terms are 7, number of outputs is equal to 2. This is one of the rough figure. We have taken totally 8 product terms, but we doesn't require this one over here. So we'll remove the last one and we'll connect this one. Now this term is what? What is the expression for this term? What is the expression for this? Like that we will proceed it up. We'll connect the fuses. Suppose the first term is A prime, we'll connect the fuse over here. B prime, okay, we'll connect the fuse over here. So wherever you are having the fuses, so this is A, this is B, this is C. So A, B, A prime, B prime, C prime. So this term is been there, and this term is been included in sum or carry. We'll check it up and we'll put that one. So the first product term, when you check it up, A prime, B prime, C. So I will be going for A prime, B prime, C for the first one. First one is, first of all, you take it as this one A, B, and C. A prime, B prime, and C. C means this one. So this is A prime, B prime, and C. Now this term is been there for the sum expression. Suppose this is sum. This is the carry. Now when you go for this one, like this way we'll proceed it and we'll be able to get a matrix of this one. We'll be getting those terms are included. And at the last we'll be having one exclusive OR gate will be connected. To the exclusive OR 0 and 1 are the inputs and we'll be getting sum and carry. The same thing has been shown over here. Implement the function F1 and F2 onto the PLA. So taking the truth table of this one, from the truth table, we will be deriving, we will be presenting on two K maps. The first K map is for F1, the second K map is for F2. Similarly, we will be taking up two more K maps onto this one. Will be when we are grouping ones over there, we take the complement of this one, inverting, changing zeros to 1 and ones to 0. Then we'll get it as F1 prime, and grouping onto this one we'll be getting F1 prime function, F2 prime function. Out of this one we'll go for comparison. Which functions if you take, it would be getting less number of literals. When you take F1, F2, F1 prime or F2 prime, according to that one, we'll be getting one list of product terms, least number of product terms which are having in a common terms. You can see if I take F1 prime and F2, I'm getting a least number of product terms. That is nothing but 4. Otherwise, I would have get 6 product terms. So it is better that I will be going for F1 prime and F2. So you will be having this PLA programming table for each of the, when you go for the PLA programming table, you can see over here A, B is there, the first product term. So you treated A, 1, B as 1 and C as dash, this one. Similarly, A, B is dash and C is 1. Like that way, if you proceed it up, you will be getting a PLA table of this one. The same PLA table is been drawn onto the PLA diagram, which is shown over here, and the interconnections for this one is been made. This is for AB and now this one. This is an OR gate for the first term. Some expression is been F1. Sorry, this is the OR gate for the first term, which is F1. F1 is having two terms, BC plus AB plus AC plus BC plus AB, three cross marks. And for this one also, AC plus AB plus A prime, B prime, C prime, which has been shown over here. The two terms will be taken into consideration. So this is F1, this is F1, and this is F2. Now this F1 is been to be connected to 1 to get enough complemented F1 prime we are taking. So to get enough function as F1 prime, we'll be connecting to there. And second function is been there as F2 only. So this is one of the example. More examples, you can go ahead with this one. PLA, very straightforward. So once again, what are the outcomes which we have been able to achieve from this lecture? You will be able to explain the PLAs and its working examples. You will be able to build Boolean functions using our PLAs. So you can go ahead with this lecture level problem, which is shown over here, F1, F2 prime and F1. So the circuit and diagram will be like this way. Thank you for watching this video, and if you want further readings, you can go ahead with the reference as Maurice Manu and RP Jain. You can go for that. Thank you.